Hi, it's me, Dr. Prasad Puthiyillam. Continue my classes on coordination chemistry, magnetochemistry, class number 3. In previous class, explained about the introduction to complexes as well as transition metals, how to write the electronic configuration, and what are the possible oxidation states of transition metal elements, D block elements, as well as F block elements, that is lanthanides and actinides. Now, continuation of introduction part, that is ligands. What are ligands? Ligands are either neutral molecule or ions or atoms or molecule. Atoms means atom or molecule. Molecule means group of atoms. So it may be an ion or a neutral. They are electron paired donors. That means these ligands, these atoms or group of atoms are able to donate electrons to the central metal atom. And based on the ability to donate the electrons as well as in the field, the presence of the magnetic field, we call it as weak field ligand as well as strong field ligand. So the ligands are classified based on the ability to donate electrons or the ability to create the field, the effective field towards the magnetic field, how it contribute, how these ligands will contribute towards the magnetic property. We call it as weak field ligand as well as strong field ligands. So if you take the examples, the metal ions bound to a strong field ligands. So if the metal ion is connected, is covered by strong field ligands, then it will be following the Aufbau principle. The filling of electrons will be following the Aufbau principle, and Aufbau principle says that the electrons will be paired first. Okay, before the electrons goes to the higher energy level, pairing takes place. That is the say roughly, if I say, that is the meaning of Aufbau principle. What is the conclusion of Aufbau principle? Whereas the complexes bound to weak field ligands follows a Hund's rules, just an opposite case of that. So if you take the examples for that, ligands example, say iodide. So that is the weak field ligand. So I'm taking the weak field ligands first, then in the increasing order of its strength. So iodide, that is the first. So if you consider the lowest, say weakest ligand, like that, if I say at present, after doing the experiments, a lot of experiments, found out that iodide is at present the weakest ligand. Okay, iodide we call it as iodo. It is having I minus, so it is a monoanionic. Anionic means negative charge is there. It is a monodentate ligand. We can form only, it can donate only one pair of electrons. So we call it as monodentate ligand. It connected to the central metal atom. The next one, increasing order, that is bromide, bromido, Br minus. Then comes a sulfide, thio, S2 minus. So it is a dianionic, S2 minus is mentioned. Therefore, it is a dianionic. It can act as both monodentate ligand as well as it can form bridging between two metal as well as any other groups or two metals. It can also form a bridging type ligand formation. Bridging like structure also it can form. The next one, that is thiocyanate, that is S-thiocyanate, where the S is given in bold letter. That means that the ligand connection takes place to S. So SCN, so it is a monodentate ligand. It can also act as a bidentate ligand. It can also act as a ambidentate ligand. Okay, ambidentate means it has got two sides which can connect to the central metal atom through nitrogen as well as through sulfur. Therefore, we can call such type of ligands as ambidentate ligand. Then comes the chloride. Chloride is a monodentate ligand. It can also form bridging structures. Then comes nitrate or nitrato or ONO2. That is the structure given. That means the ligand forms or ligand that a connection, the coordination bond forms with the oxygen, not with nitrogen. Then comes azide, azide or azido. Okay, here also N is capitalized. That means connection to this N. It is a monodentate ligand, but this azide or azido, they are very toxic in nature. Then comes fluoride, F minus. Then hydroxide, hydroxido, OH minus. It is a monodentate ligand, hydroxide, but it are also found as a bridging ligand too. Then comes oxalate, that is OCO, COO 2 minus. So 2 minus means it is a dianionic. Okay, so it is a dianionic case. Then comes water. Water means aqua, OH2. Okay, or single bond H, single bond H. Here I mentioned as OH2. Okay, so it's a neutral ligand. It's a monodentate ligand. Then comes nitrite, nitrito, ONO. It is an ambidentate ligand. Okay, it can form linkage to a two atoms can form the linkage. Therefore, it is a you can address monodentate as well as ambidentate. Then acetonitrile or acetonitrilo CH3CN, which is neutral. Pyridine, ammonia, ethylene diamine, NH2 CH2 CH2 NH2. And ethylene diamine, it is a bidentate ligand. 110 phenanthroline OPHEN C12H8N2. Then comes cyanide, CN. Cyanide also it's a monodentate ligand. It can also form a bridge between metals. Then last comes carbon monoxide or carbonyl, CO. So it is a neutral ligand. It's a monodentate. Also it can form bridge structure. So that's about the uh, increasing order of these ligands. Okay, from weak field ligand to strong field ligands. So if you consider this increasing order or decreasing order, if you consider, we call it as spectrochemical series. So spectrochemical series, some of the important spectrochemical series, some of the important one which is very easy to remember or which comes in question paper. Whenever you solve a question paper, most of the cases this type of ligands will come. Therefore, you should remember this: I minus, Br minus, Cl minus, F minus, OH minus, H2O, NH3, NH2 minus, Cn minus, in which I minus is the weak field ligand, then it increases in the order, and Cn minus is a strong field ligand. Okay, now in coming classes, I'll be using the word strong field ligand or weak field ligand. Okay, so should remember this order. We should know what is the meaning of that weak field ligand. If it is a weak field ligand, what we said, weak field ligand will what we mentioned there, that weak field ligand will follow the Aufbau principle and the Hunt's rule. That also should remember. So I'll take back that one. Okay, so you mentioned here that the strong field ligand follows the Aufbau principle. That means if it is a strong field ligand, it will follow the pairing takes place. And if it is a weak field ligand, then pairing will not take place. So that will contribute towards the magnetic property of our coordination complex. So you should remember that those terms also. Okay, so I'm coming out from the presentation. Thank you very much for watching. Next class will come up with the type of magnetic behavior of coordination compounds.